Welcome back. Today we're jumping straight into a classic WAEC Mathematics challenge. In this explainer, we're tearing down a specific question from the 2025 practice set over at QandAHelp.com. If you want to walk into that exam room totally bulletproof, well, you're in exactly the right place. We're going to break down the mechanics of inverse variations step by step, so the next time a question like this pops up, you won't even break a sweat. Let's get right into it. Okay, let's take a look at exactly what we're up against today. The problem says a variable p varies inversely as the square of q. If p equals 5, where q equals 6, find q when p equals 1.8. And then we've got our four standard options: a is 5, b is 10, c is 15, and d is 20. Now with math like this, you know the drill. Every single word and number is a deliberate clue. We've got an initial state, a final state, and a very specific relationship between those two variables. So the absolute most critical phrase in that entire sentence is varies inversely as the square. When you're sitting in the exam hall, your brain needs to instantly translate those English words into a math equation. Varies inversely as the square literally just means p equals k over q squared. That k sitting right there on top of the fraction, that's our constant of variation. It's the anchor. It's the one unchanging number tying p and q together. And finding its value is always, always mission number one. Actually, before we start crunching these numbers, let's think about what this equation actually means in real life. Inverse variation is kind of like sharing food. Imagine you've got this massive, delicious pizza. As the number of people sharing it, let's call the people Q, goes up, the size of your individual slice, which is P, gets way smaller, right? And because it varies inversely as the square of Q, as the crowd grows, that slice shrinks incredibly fast. It's an accelerated drop. Q goes up, P absolutely plummets. All right, let's look at the actual numbers they gave us to work with. The question tells us that P is 5 when Q is 6. So what do? We take those exact values and plug them straight into our formula. Substituting them in, we get 5 equals k over 6 squared. Basically, we're setting a trap to capture our constant k. We know both the variables for this specific moment, which leaves k as the only unknown we have to solve for. Let's walk through the algebra here, nice and easy. First up, we square the 6. 6 times 6 is 36, so the equation simplifies to 5 equals k divided by 36. Now, to get that constant k all by itself, we've got to eliminate the denominator. We just multiply both sides by 36. That perfectly isolates our variable and leaves us with super straightforward math. K equals 5 times 36. And boom, there it is. 5 times 36 gives us exactly 180. We just found our constant of variation. So k equals 180. Take a mental snapshot of that number, because it's literally the key that unlocks the whole rest of the problem. Remember, no matter how wildly p and q bounce around in this specific question, k is stubbornly gonna stay right at 180. Now, armed with that constant, we can jump right into the second half of the question. They want to know the new value of q when p changes to 1.8. So we go back to our original formula, but this time we know for a fact that k is 180 and our new p is 1.8. Plug those in, and here is our new equation. 1.8 equals 180 divided by q squared. So now we just have a brand new unknown to solve for. Let's just rearrange things to solve for q. First, to clear that fraction and make this look a bit cleaner, we multiply both sides by q squared. That gives us 1.8 times q squared equals 180. Next, to get q squared totally by itself, divide both sides by 1.8. And 180 divided by 1.8, well, that gives us a wonderfully clean number. We're left with q squared equals 100. And we are right at the finish line. If q squared is 100, we just take the square root of both sides. The square root of 100 is 10, so our final answer for q is 10. The trap snapped shut and we got it. Honestly, when you break it down and just follow the algebra step by step, the complexity of these variations completely melts away. So, checking back with our original WAEC options, A is 5, B is 10, C is 15, and D is 20. We can confidently lock in option B. We took the traditional path here, identified the relationship, found our constant from the initial state, and used it to solve the final state. It is highly systematic, and, well, it works perfectly every single time. Now, what we just did was the traditional method. It's solid, it's what textbooks teach you, and it builds a great foundation. But listen, time is literally your most precious resource in an exam. So what if I told you there's an incredible time-saving shortcut? Because our k is always constant, the product of p and q squared from the first scenario will absolutely always equal the product of p and q squared in the second scenario. That gives us this beautiful, super efficient formula, p1 times q1 squared equals p2 times q2 squared. Let's actually see this shortcut in action. By using this, we completely bypass having to find that constant k. We just skip the middleman. Look at the numbers. We take our state 1 values, where p is 5 and q is 6, and our state 2 values, where p is 1.8 and q is unknown. We plug them directly into the shortcut. 5 times 6 squared equals 1.8 times q squared. Everything we need to solve it is sitting right there in one single elegant line of algebra. Check out how incredibly fast this is. 6 squared is 36, and 5 times 36 is 180. So right away, 180 equals 1.8 times q squared. Divide by 1.8, and boom, q squared equals 100. Take the square root, and q is 10. You see that? We arrive at the exact same answer, option B, in a fraction of the time, with way fewer steps to potentially mess up. During a high-pressure exam, a shortcut like this is an absolute lifesaver. Now, the crucial part of learning any new math trick is proving you can actually use it. So let's do a quick quiz to really lock this in. Here's your challenge. If y varies inversely as x squared, and y equals 4 when x equals 3, what is the constant k? Just take a quick mental pause, picture the initial formula in your head, and think about exactly where those numbers need to drop in. All right, let's see if you nailed it. Here's the step-by-step breakdown. The base formula for inverse square variation is y equals k over x squared. Putting our numbers in, we get 4 equals k over 3 squared. Since 3 squared is 9, that's 4 equals k divided by 9. Multiply both sides by 9 to isolate k, which gives us 4 times 9. So your constant k is exactly 36. If you got that, you're doing fantastic. Your algebraic foundation is rock solid. Okay, I want to throw one more challenge your way, and this time I strongly urge you to use that time-saving shortcut we just learned. Try this. For an inverse square variation, if p1 is 2, and q1 is 5, and p2 is 0.5, what is q2? Think about that P₁Q₁² formula. Let's see if you can skip the constant entirely and jump straight to the solution. Let's walk through the shortcut together and check your work. The formula is p1 times q1² equals p2 times q2 squared. We substitute our numbers. 2 times 5 squared equals 0.5 times q squared. 5 squared is 25, and 2 times 25 gives us 50 on the left. So 50 equals 0.5 times q squared. Divide 50 by 0.5, which, by the way, is exactly the same as multiplying by 2, and you get 100. Q squared is 100, which means our q2 is 10. Nailing the correct answer efficiently like this should give you massive confidence heading into test day. What an awesome session today. You just mastered a critical inverse variation problem, grasped the real-world concept behind it, and added a massive time-saving exam shortcut to your toolkit. I love the motto from our source material today: practice smarter, pass with confidence. I highly recommend checking out QandAHelp.com for more of these step-by-step WAEC, JAMB, and GCE preps. Before we wrap up, I want to leave you with one final thought. If you were able to learn this incredibly powerful math shortcut in just a few minutes, imagine how many other exam-saving tricks you're currently missing out on. Keep learning, keep practicing, and I'll catch you in the next explainer.